Hello, Algebra 1 students. Back to music with lyrics. We're going to listen to fun today as we learn about applications of quadratics. So, I know you don't like word problems, but it's kind of irrelevant. It's important that we know how to solve them. So let's talk about why we use equations to solve word problems. First and foremost, efficiency. You may not be super efficient with this now, but in the long term, this is what's going to make you a more efficient problem solver. And it's not just about doing math in order to pass a state test. It's also about being able to apply the math in the real world. Remember that the people who are coming out of college and making the most money are working in things like computers and in things like higher mathematics. And it's not because they're going into grad school. It's not because they're going into teaching. Let me tell you, it's definitely not because they're going into teaching, making money. It's because they're going into finance. And the problems that you have to be able to solve are going to be pretty complicated in order to make it work that way. Now, not all of you want to go into finance, but if that's something you're interested in because of the money, you need to have this skill. You cannot just sort of putz around until you find an answer. And that brings me to my second reason, consistency. If you can write an equation, you can solve it. You now know how to solve linear equations, quadratic equations, systems of linear equations. Okay, it's not a big stretch to get you to systems of quadratic equations, which we won't do this year, but you will in Algebra 2. Okay, now, there's two basics to this, these two. Name the smallest unknown and build on that to name the other unknowns. Write the relationship out in words to figure out how to construct the equation. Okay, words or symbols, really. Let's get started. We have two that we're going to write equations for, and then two where I give you the equation and you've got to figure out what it is that you need to solve. All right, let's take a look. Starting with a consecutive integer problem. Consecutive integer problems are usually pretty straightforward, so we're starting with a simple one to get us back in the habit of writing equations for word problems. Let's read. Find three consecutive integers that are positive and odd, such that the product of the first and third is 4 less than 7 times the second. So let's start with naming our integers. Our smallest one is indeed going to be x, so let's start with that. X is going to represent the first integer. How do I represent the next or the second integer if the next integer we're looking for is also odd? Well, if the first one is odd, how do you find the next one? It'd be x plus 2, because the next odd number is 2 more than the first. How would you represent the third integer? Sorry about that. How would you represent the third integer? Be x plus, not 3, but 4, because it's 2 greater again. So think about odd numbers. Think about odd like 1. The next odd number is 3, 1 plus 2. And the next odd number after 3 is 5, 3 plus 2. Okay? Let's map it out. The product of the first and third. So we have the first integer times the third integer on one side. Is my equal sign. 4 less than, so that's minus 4. 4 less than what? 4 less than 7 times the second integer. There's our equation written in symbols. Let's now put in the expressions that we got when we wrote this all out in the first place. The first integer is x. The third integer is x plus 4. So we're putting those in those spots. Then we have 7 times. Second integer is x plus 2. And then a minus 4. We're going to distribute and solve. Now right here, this is what makes this a quadratic equation, is that when we distribute there, we get an x squared. Not on this side though. So x squared plus 4x equals 7x plus 14 minus 4. So 14 minus 4 is 10. So I have x squared plus 4x equals 7x plus 10. I'm going to subtract both the 7x and the 10 from the right side so that I get one side equal to 0. 4x minus 7x is negative 3x, so negative 3x squared minus 3x, negative 3x, minus 10 equals 0. So x squared minus 3x minus 10 equals 0. Factored form. Factors of negative 10 that add up to negative 3 are negative 5 and positive 2. Use your zero product property to finish. X minus 5 equals 0, so x equals positive 5. X plus 2 equals 0. So x equals negative 2. Now, the x equals negative 2 is not possible because from the beginning they told us we were looking for positive odd integers. 2 is even and it's negative, so neither of those will work there. So what are my integers then? If x equals 5, The integers are 5, 5 plus 2 or 7, and 5 plus 4 or 9. So 5, 7, and 9. Not too stressful. Be prepared to do one like that in class. Let's look at another type. Draw a picture. A frame for a picture is 2.5 inches wide. The picture enclosed in the frame is 5 inches longer. Oh, I'm not using my little pointer. A frame for a picture is 2.5 inches wide. The picture enclosed in the frame is 5 inches longer than it is wide. If the area of the picture itself is 300 square inches, find the outer dimensions of the frame. Okay? So let's draw it. There's the frame, the outside of the frame. There's the actual outside of the picture. Okay, it's not perfect, but you catch my drift. Let's do some labeling. Well, what do we know? We know that this area in the center here is 300 square inches. And we know that this border, the frame itself, is 2.5 inches wide. All right, the other thing we know is that the frame is 5 inches longer than it is wide. So name the width x. If the length is 5 longer than that, then it's x plus 5. All the way across. So x plus 5 all the way across. Okay. All right, so now we write our equation. Now, area. How do you find the area of a rectangle? Well, it's length times width. Oops, sorry. Length times width equals area. Well, the length is x plus 5, and the width is x. And the area is 300, so there's our equation. That's what we're going to solve. So we're going to distribute this x to both terms in the parentheses. So x squared plus 5x equals 300. We're going to subtract the 300 from both sides to see if we can factor it, which we can, because I used happy examples. So equals 0 on the other side. Factor that. We're finding factors of 300 that add up to, factors of negative 300 that add up to positive 5. So I'm going to start with positives. How about 10 and 30? No, that can't be it, because that would have a difference of 20. How about 20 and 15? Hot dog, that's it. Making the 15 the negative. So x plus 20, x minus 15, giving me zeros of negative 20 and positive 15. And as we had in the previous problem, the negative is not going to work because we can't have a negative dimension. But the positive definitely works, and the positive is the one we want. So if x is 15, then the dimensions of the photograph are 15 by 20. But we don't want the dimensions of the photograph. We want the dimensions of the entire frame with the photograph in it. So we need this 15 plus the frame, and this 20 plus the frame all the way out to the edges. So plus 2.5 on either side, and the same thing up here, plus 2.5 on either end of that side. So each one is going to add 2.5 on each side, so each one's going to add 5 to it. So if the photograph is 15 by 20, the frame is 20 by 25. 20 inches by 25 inches. And that's our answer. 2 more, now you'll actually have the equation given to you. So let's look at that. Using zeros to solve. So an object is launched from 19.6 at 19.6 meters. Oop, typo. Meters per second from a height from a 58.8 meter tall platform. The equation for the object's height in meters, s of t, not just s, at time t seconds after launch, is given there. When does the object strike the ground? Let's draw a quick picture for this. We know it's a sad parabola. We don't need a graphing calculator because we're not going to do it that way. We know it's a sad parabola. We know that we're looking for when the object strikes the ground. Well, t is your horizontal, and s of t, which is the height, is the vertical. So t is the time, and that's what we want. We want to know when it strikes the ground. Now, we don't want this 0, though, because that 0 is actually impossible in this circumstance because that would be going negative time. Can't have that. We want this 0. So we're trying to find the x value of this 0 right here. So let's find the zeros. So we have to take our equation. Okay, we have to take our equation And we've got to set it equal to 0 instead of S of t equals 0. And what we're going to need to do with it is to start off, let's go ahead and divide everything by negative 4.9. Because I know you're looking at this thinking, ugh, gross. It's going to work out so nicely when we divide. Look what we get. Negative 4.9 divided by negative 4.9 gives me 1t squared. 19.6 divided by negative 4.9 gives me negative 4t. And 58.8 divided by negative 4.9 gives me minus 12. Look how nice it turned out. See, you never know. If you get rid of that coefficient, divide it off, since it's an equation, and we're allowed to do that when we're solving an equation. We're not just factoring. And I don't want to factor it with the decimals. That's just like torture. That's not happening. I know it's 1 plus, 1 minus, and I know my factors are factors of negative 12 that add up to negative 4. It's negative 6 and positive 2, giving me t values of 6 and negative 2. As before, negative's not going to work because it's time. So 6 seconds. So when is it going to hit the ground? 6 seconds after the throw. 6 seconds after the throw. Awesome. Last one. As evidenced by the title, we are not using the zeros to solve. This time we're using the vertex. Let's read. An astronaut on the moon tosses a ball into the air. The height of the ball is represented by this equation right here. The variable t represents the time in seconds again, since the ball was thrown, and f of t represents the height of the ball in feet. To the nearest tenth of a foot, what is the maximum height the ball achieves? I almost said achieves. Sorry, I'm not sure why I would say it that way. All right, so again, we have a parabola. Okay, and again, really, in reality, we're not addressing any of this. This doesn't actually happen. So we're really only talking about from here over. Where's the maximum height? If this is the path of the ball is going splat. If this is the path of the ball, where's the maximum? It's the vertex. And that's an ordered pair. We know that. Are we looking for the x of the vertex, which is the time to that point? Or are we looking for the y of the vertex, which is the height at that point? We're looking for the height at that point. So we're looking for the y value of the vertex. So we don't have to think about solving this at all. We just have to know how to find the vertex, which we just reviewed in class. How convenient. The opposite of b over 2a. Opposite of 13.5 over 2 times negative 2.7. And that's an x equals. That gives you the x value of the vertex. Okay? And when you simplify that down, you get 2.5. Now, how do I find the height at the vertex? Plug in the 2.5. So I'm taking my equation, and I'm plugging in a 2.5 for x. Now, clearly with the decimals, this is a circumstance where it's probably just easiest to use a calculator. So hopefully you have a calculator handy, or you can switch to your graphing calculator app. I'll punch the buttons here on mine. So negative 2.7 times 2.5 the quantity squared plus 13.5 times 2.5 plus 14, enter. I get 30.875, but they want me to round it to the nearest tenth of a foot. So 30.9 feet is the maximum height of the ball. Not that bad. Okay, you know you're going to miss these videos. You know you are. But this one's done. So you're going to have to go ahead and start by missing this one. See you guys in class.